Hello everyone, welcome to lecture 1.3. We will be covering portability and scalability in heterogeneous parallel computing. The objective of this lecture is for students to understand the importance and nature of scalability and portability in parallel programming and how they are related to the software cost. This slide shows an IBM data on software versus hardware cost in system design. In this picture, the software cost is measured with the number of software lines per chip. It's shown as the red line, and it increases at 2 times every 10 months. And the hardware cost is measured by the number of gates per chip, which is shown as a blue line, and it increases at 2 times every 18 months. The software costs crossed over and overtake the hardware costs near 2008. We are at the point where the software costs significantly outweighs the hardware costs in pretty much all the system designs. Now that we understand the importance of software cost, we're going to introduce the first aspect of software cost control, scalability. Scalability means that if an application runs well on a core A, it should also run well on an improved version of core A. Let's say if the vendor introduces the second version of core A. And software scalability also means that when an application runs well on one core A, it should be able to run well on 2 core A's, 3 core A's, or even more number of core A's. And essentially, it should be able to make full use of the available number of cores and continue to increase performance. We have introduced the number of cores as an important dimension of scalability. With each generation of new hardware from vendors, we also see increasing number of threads, vector length, pipeline depth, DRAM burst size due to the increasing ratio between interface clock and DRAM core clock, number of DRAM channels, and increasing data movement latency because of the increasing system size and complexity. Now we introduce the second aspect of software cost control, portability. Portability means that if an application runs well on core A, it should also run well on some different types of cores, such as core B and core C from different vendors. And if the software has good portability, then a user should be able to use the same software on multiple hardware from different vendors and still get good execution results. Sometimes it also means that different vendors often use different styles of design. Some vendors may be using traditional CPU design. Some vendors may be using VLSW design. Some vendors may be using digital signal processing design. Sometimes some vendors may be using GPU style design. And the application should be able to run well across these different design styles. In summary, portability has also several dimensions. We mentioned the portability across vendors, and oftentimes vendors will have different instruction set architecture, such as x86 versus ARM. We also should see good portability between design styles, latency-oriented CPUs versus throughput-oriented GPUs. With good portability, we expect the software to run well across parallelism models, VLSW versus SIMD versus threading. And last but more also quite important, is that oftentimes we need to have the software to run well across memory models, whether the cores have shared memory or they have distributed memory of their own. This concludes Module 1.3. Thank you.